Right, hi, AP Chem students. We're going to be looking at the stoichiometry review questions today and notes in PowerPoint. Let's take a look here. What are we going to be accomplishing through this particular set of slides? So this is 4.5 topic on the College Board CED, the course and exam description. It's only half of the topic, though. We're going to revisit stoichiometry when we get to limiting and excess reactants. But for the start here, we're going over the basics, and let's take a look here. The enduring understanding is when a substance changes into a new substance, or when its properties change, that no mass is lost or gained. So that's the enduring understanding that we need to be keeping in mind as we're looking at our stoichiometric problems. The learning targets. I can explain how chemical equations support the law of conservation of mass. That's important right here, that law of conservation of mass. Identify a mole ratio. That's a major component here of this particular one, and using the balanced chemical reaction to identify that mole ratio. Perform stoichiometric calculations. Going to be doing a lot of those as well. And calculating percent yield. All right, so let's briefly talk about what stoichiometry is. It's the study of quantitative relationships between the amounts of reactants. So the amounts of the reactants are important, and the products formed, those amounts, by a chemical reaction. The reason why stoichiometry works is because it's based on the law of conservation of mass. Okay, the law states that matter is neither created nor destroyed in a chemical reaction, which is part of the reason why we have to balance those chemical reactions with the coefficients in front to make sure that we are not creating nor destroying any kind of matter. Chemical bonds and reactants break and new bonds form to produce the products. Okay, so you do have bond breaking, bond forming, new substances forming, and there's an energy exchange in there. That's going to be under another topic. But the amount of matter present at the end of the reaction is the same as it was at the beginning. So you don't lose matter, you don't gain matter. So it's not created or destroyed, not gained or lost. However, it is altered and just in a new form, in a new substance. Therefore, the mass of the reactants should equal the mass of the products. So we're going to demonstrate the law of conservation of mass using stoichiometry here and proving that this is why it works with our next example. Before we get on to the example, though, you will need a periodic table for this particular set of problems because you're going to need to be able to look up the molar masses of the elements. So definitely go ahead and click on the link, pull up, this is the College Board's periodic table that we're going to be using throughout the year. Remember, you need to become very familiar with the symbols. They don't provide you the names, and this is going to be the periodic table that they allow you to use on the AP exam. All right, so looking at our law of conservation of mass. This is a really great example, and I really like this chart because it kind of sets everything up for you. All right, so we have our reaction here. We have iron metal reacting with oxygen gas here, and it's going to produce iron 3 oxide, which is better known as rust, by the way. That's the red stuff that you see on your metal, that brown red stuff. So iron 3 oxide produced by iron reacting with oxygen. Now we balance the equation here with our chemical formulas, Fe being iron, O2, remember, is diatomic oxygen, it's elemental oxygen. Remember the other diatomics, we have Brinkelhoff here. It's a good way to remember the other 6 elements too that are also diatomic in their elemental states. That means they exist as twins, as 2, so Br2, I2, N2, Cl2, H2, O2, and F2. These are the only elements on the periodic table that exist this way, where we call them diatomic. So just a quick little review of that information there. Oxygen, of course, being one of the diatomic molecules. elemental molecules as well. So iron plus the oxygen gives us the iron 3 oxide, the rest. Now, as you can see by the balancing these coefficients here, you need 4 of the iron, 3 of the oxygens to get 2 of the iron 3 oxide. So that's the balanced equation. And we'll touch on balancing later, but for right now, we're just going to use what is provided, the already balanced equations in the problems. So one way of representing this is saying that it's 4 atoms of iron plus 3 molecules of oxygen, giving us 2 formula units of our iron 3 oxide. Now remember, formula unit is the word we use for ionic compounds. Ionic compounds are always metals plus nonmetals, or they might be polyatomic ions in there, but we always use this designation formula unit to represent ionic compounds. So, because these counts are the way that they are, we know that the mole is a counting unit. We're going to now translate it into mole terminology. So, we're going to say that 4 moles of iron plus 3 moles of oxygen is going to give you 2 moles of iron 3 oxide. So the counting unit mole now translates over, and we can use it in our calculations and set up our t-charts and put it in as our labels as the correct way to go between different substances in a chemical reaction. In this case, we have 3 substances in our chemical reaction. We have iron, oxygen, and iron 3 oxide. So we'll be looking at the mole relationship between them in order to switch around and go from reactant to product or product to reactant. This case, we're going to prove the law of conservation of mass by looking at the moles of each substance in the reaction and calculating their masses. So it's going to take a one-step conversion t-chart by doing that. So we're going to set up the first one. We have 4 moles of iron. So you take those moles of iron and you diagonal them down. And we're going to go to grams since we're looking for the masses here, proving the law of conservation of mass in this particular problem. So now we need the periodic table. You look on the periodic table and what you'll notice is that iron happens to be 55.85. And we put the 1 mole on the bottom so we can convert using our molar mass here. The moles of the iron do cancel like you see right here, and so then we're left with the grams of the iron. What ultimately happens here, you calculate it, and as stated before in class, I just wanted to make sure everybody understands when we're working with molar masses from the periodic table, we only go out 2 decimal places, out to the hundredths. That way it's standardized for everybody and we're all using the same molar masses. So make sure that you round to 2 decimal places for your molar masses. Now 3 moles of oxygen here, doing the second reactant. We're going to take those moles of oxygen, diagonal them down because we want to cancel out the moles of oxygen, and we're going to put the grams on top because that's what we desire. The desired amount goes on top. And the molar mass of oxygen happens to be 16, and there's 2 of them, so you'd multiply 16 times 2. Okay, so then we multiply our 3 times our 32 to get the mass of the oxygen, which happens to be, canceling out the moles of the oxygen, 96 grams of oxygen. So far we've calculated the masses of each of the reactants here. Now we're going to look at the mass of the product, the iron 3 oxide. Setting it up in such a similar fashion where we put the moles, we're going to diagonal them down here to cancel out the moles. I'm going to put the molar mass of the iron 3 oxide on the top. Now remember, for molar masses here, if we have 2 irons at 55.85, and then we have 3 oxygens at 16, all you have to do is multiply those. Here's the iron, here's the oxygen. Multiply those, add them up, and you should end up getting the 159.7. Once again, we cancel our moles of iron 3 oxide, multiply the 2 times the 159.7, and we end up with 319.40 grams of iron 3 oxide. Still going out 2 decimal places on our molar masses. Now, let's see how that adds up. If we have 223.40 grams of the iron, 96 grams of the oxygen here, and 319.4 grams of the iron 3 oxide. According to the law of conservation of mass, the masses should add up from the reactants over here to the products on this side over here. Not created nor destroyed. Let's make that A a little bit better. All right, so let's add it up and see. Reactants and products. And I can erase that. And the product, it is just one product. Okay, adding these two values together, what you'll see here is it does end up being 319.4. So the masses do match, and they should match according to the law of conservation of mass. This is how you would prove, of course, the law of conservation of mass works here, and this is why the stoichiometry is going to work. Now, you might see an occasional law of conservation of mass type problem where they give you, say they gave you the mass of the iron, they gave you the mass of the iron 3 oxide, and you would need to figure out the mass of the oxygen, but as you can see, they should just add up on both sides. We'll also be using this concept when we're trying to figure out our combustion analysis empirical molecular formula problems. We did some of those last year in Chem 1. And we will be revisiting that topic later, but you'll see that this concept of law of conservation of mass will pop up again. All right, so now looking at the stoichiometric map here, the stoichiometry map, where we have a series of different conversions to happen. Now I'm going to add one over here because we can do liters of any gas at STP. For A, you can start with liters depending upon what the if it's a gaseous substance. You can also work it to liters if you want to of any gas at standard temperature pressure for B. And we're going to go back over this conversion in just a moment, but it is something that you can work to on either side of the stoichiometric map here. Now A is for the given substance, B is for the desired substance. So you can start anywhere on this map here, like you could start with the grams of A and then work to moles of B. You could start with moles of A and work to particles of B. We're going to use the map to help us figure out where we need to start, where we need to end. All right, so looking at the first example of stoichiometry. Okay, multimole problems involves using the mole ratio. We're going to be using that mole ratio. And this one should only take you one step to complete the conversions. Now, how many, we have 12 moles of water. How many moles of oxygen are needed? Well, let's take a look here. We have 12 moles of water, and we're looking for moles of oxygen. So what you can do, if you need to, is cross out the other components of the chemical reaction, the other substances. We don't really need to worry about methane. This is ethane, excuse me. We don't need to worry about ethane. We don't need to worry about carbon dioxide because it's not part of our problem. So we're going to ignore those two and only focus on the water and the oxygen. Now this is our given amount, so this is going to be that A on the stoichiometric map. And then we're going to have, going to the oxygen, that's going to be the B on the map. So as you can see, we're going to point to it. This is our moles of A. Now that means this part of the map over here we don't really need, so we're going to black it out because we're not starting with grams or particles or liters, we're starting with moles. So this is where we would start. And where are we working to? Well, we're working to moles of B. So as you can see right here, then that means we don't really need this part of the map either because we're not going to particles, grams, or liters. So we're going to black that out. So this one's going to take one step. You have one conversion, and it involves using the mole ratio. Okay, so set up your T-chart. Now, if we need to get rid of the moles of water, we need to diagonal that down. Now, this is the part about using the balanced reaction to find the mole ratio. So looking at those coefficients in the balanced reaction, you're going to look for up here, the 6 and the 7 right there. Those are our coefficients in the balanced reaction. And we're going to insert those numbers next to their substances in the T-chart. So the 6 is going to go next to the water on the bottom. The 7 is going to go next to the oxygen on the top. And then therefore the moles of the water should cancel. And we're left with our moles of oxygen. Multiply and divide, so 12 times 7. Then you divide it by the 6 on the bottom, and you end up with 14 moles of oxygen. So far, so good. One-step problems involve just doing the mole ratio. It's mole to mole. You'll see that this is the most basic of the stoichiometric calculation problems that you'll see. All right, so looking at example 2, which is a mole to mass problem. Now, what you should also realize when we're looking at this example, this mole to mass is going to take 2 steps. Okay, now anything that has mole to something or something to mole, so we could be doing particles to mole, could be doing liters to mole, you could be doing moles to particles. Anything where it's something to mole or mole to something, it's going to take you 2 conversion steps to get there. In this particular one of the main components of pearls is calcium carbonate. If pearls are put in an acidic solution, they dissolve according to the equation below. How many grams of calcium carbonate can be dissolved in 0.0250 moles of hydrochloric acid? So let's look here. We're starting here with our hydrochloric acid, 0.0250 moles. And we're going to our calcium carbonate. So that means the other components of the chemical reaction we don't really need to look at. So calcium chloride, water, and carbon dioxide we can cross out or completely ignore at this point. Now looking at our map, where are we starting and where are we going? We're starting with moles, so that means we can black out the moles or the particles in grams of A. And we're going to grams of the calcium carbonate. So that would be this component over here. All right, we're going to go 2 steps. So this is the first step, and then this is the second step here. So we got to go to the moles of B and then to the grams of B. Set up your T-chart, okay? Now, once again, we need to get rid of these moles of hydrochloric acid, so they're going to diagonal down. Then right here, we're going to get rid of the moles of the calcium carbonate, diagonal those down, and then we ultimately end up with our grams of calcium carbonate. Now the first step here is going to be the mole ratio step, because we're going from the hydrochloric acid to the calcium carbonate, so we're going to need those coefficients in the balanced reaction. So let's take a look here. There's a 2 in front of the hydrochloric acid, so we're going to use that number to put on the bottom. But there wasn't a number in front of the calcium carbonate. So remember, when there is no number in front of a substance, it's an understood 1. So we're going to put those in there. Now we need the periodic table because we need to look up calcium carbonate's molar mass and calculate that. So we look up calcium. Calcium is 40.08. Then we have carbon, which is 12.01. So here's calcium, here's carbon, and then oxygen. So oxygen is 16, but there's 3 of them, so we need to multiply that by 3. Once we do that, we can add all that up and get our molar mass of calcium carbonate. And that value ends up adding up to 100.09. Okay. Now that we have it all set up, we can look at the canceling. So the moles of the hydrochloric acid cancel. The moles of the calcium carbonate cancel, and then we're left with grams, which is what we want anyways, of the calcium carbonate. Then we multiply everything on the top, okay, so the 0.0250 times the 100.9, and on the bottom, it's 2 times 1, so really divide by 2, so divide by the bottom. And we end up having 3 significant figures here, okay, don't forget sig figs, because if you're looking at this number, starting number, And following significant digit rules, it's the first non-zero digit that counts and then everything after it. So this one has 3 significant figures. That means we want to keep 3 significant figures in our answer. And make sure that you're always looking for rounding your answers according to significant figure rules. In AP, they usually give you a little bit of leeway, plus or minus 1 sig fig, and that's how I'm going to follow too, but you do have to make an effort to try and at least round it. The other thing I want to see in your answer is the unit and the substance. So don't forget to tack on the unit and the substance when you're doing these problems. All right, the example number 3 is a mass-to-mass problem, and I call it the something to something type, where you don't have mole at all in the problem. You're going to go through the mole when you do the conversion, but it could be liters to particles. It could be particles to mass. It could be liters to mass. It's something to something, and the something to something ones are always going to take at least 3 steps, okay? So we're going to look at this particular example. When copper reacts with silver nitrate, according to the equation, what will the number of grams of copper, okay, that's important, what will be the number of grams of copper required to produce 432 grams of silver? So these are the substances that we need to focus on, the silver and the copper. So here, this is our given information, 432 grams of silver. Where are we going? Over here to the grams of copper. So we don't really need to worry about the silver nitrate or the copper to nitrate in the problem, in the bounce reaction. Now looking at our mole map, where are we starting? Well, we're going to be starting all the way over here at grams of the A, or the given information, okay? And then where are we going? We're going to be going all the way over here to grams of B. So as you can see, this is going to be one step here. This will be the next step, and then the third step in the conversion. So we're going to transfer or convert, excuse me, convert is the better word, convert the grams of silver to moles of silver. Then we're going to use the mole ratio to convert the moles of silver to the moles of the copper. And then we're going to do one more conversion where we convert the moles of copper to the grams of copper. So that's kind of how you set up the sequence here. Now you're going to insert your T-chart and then do the diagonal downs. The grams are going to go here, the moles going to go down here, the moles of the copper down there, and so forth. Now we have everything set up to cancel appropriately, and we can insert the conversion factors. Well, if you look at the periodic table for the grams of silver, that's going to be 107.87. Okay, that's going to equal 1 mole of the silver. And now we're doing mole ratio. Okay, here's the mole ratio. So we need the balance equation. Look up here at your silver, look up here at your copper. Okay, so once again, we have a 2 for our silver and then an understood 1 for the copper. So you would insert those into the appropriate spot, the 2 going next to the silver, the 1 going next to the copper, right here. Last conversion, we need to change the moles of copper to grams of copper. So once again, we need the periodic table to look up the mass of copper. And if you look up the mass of copper, 1 mole of copper will equal 63.55 grams. And now we have it set up for everything to cancel. So the grams of the silver cancel, the moles of the silver cancel, the moles of the copper cancel, and then we're left with our grams of copper, which is what we wanted. And that ends up being 127 grams of copper. If you multiply your 432 times your 63.55, then you divide by 107.87. I usually divide it first by this, and I hit enter on my graphing calculator. Then I divide that answer by 2. You could do it a different way, though. You could put parentheses on the bottom and have them multiplied together within those parentheses. But do watch your order of operations on these graphing calculators, because if you don't put the parentheses in the right spot, sometimes the calculator gets confused and it doesn't follow the correct order of operations, and then you'll get the incorrect answer. So multiply the top, multiply the bottom, divide it out. You can use parentheses, or you can use that step method where I multiply everything on the top, then I hit enter, I divide by the first answer, then I hit enter again, I divide by the second one on the bottom, and then go and get my final answer over here at 127 grams of copper. Unit substance. Also, this has 3 significant figures, so our answer is going to have 3 significant figures. Now, one quick thing I'd like to do is review the mole map here for that last conversion factor that I was talking about earlier, those liters of gas at standard temperature pressure. So at standard temperature pressure, the volume of any gas that equals 1 mole is always going to be 22.4 liters. Now, we will prove this later using our ideal gas law, PV equals nRT, but we don't really need to worry about that number or deriving that number just yet, because we'll get to that when we get to gas laws. But using the ideal gas law, you would see at standard temperature pressure, you're always going to get 22.4 liters. That equals 1 mole. Now, what is standard temperature pressure? Let's review that information real quick. Standard temperature happens to be 0 degrees Celsius or 273 K. If you're looking at it in kelvins, that's going to be standard temperature. So the freezing point of water, I guess, is the basis for standard temperature. Standard pressure, though, happens to be 1 atmosphere or 101.3 kPa, kilopascals, or 760 torr/millimeters of mercury. Now, these values, I believe, are all on your formula sheet for you to look at. They do list them. But knowing that this is standard pressure, and what is really standard pressure a measure of? It's the measure of the atmospheric pressure at sea level. So we're almost at standard pressure here in Centerville because we're very close to sea level. But this 22.4 value works at standard temperature pressure. It's always going to come out to being 22.4 liters of any gas. So reviewing, you pretty much, I think, have molar mass down, but the particles too, I want to review one quick thing about Avogadro's number. Avogadro's number, we're going to use that a little bit too throughout the calculations. You can recognize it as Avogadro's number if you see atoms, ions, formula units, or molecules next to the number. And the number is usually going to have some kind of 10 to the 20 something power in it. Now, the representation for atoms comes from it's representing elements off the periodic table. Now, if it's an ion, it's representing some kind of charged element off the periodic table, like copper 2, or say aluminum, which is a +3, or how about sulfide, which is S2-. So all of those would be considered to be in the ion category. Now, formula units I talked about a little bit earlier, those are for ionic compounds. So that's always going to be metals and non-metal compounds. Or if you see polyatomic ions in there, like nitrate, ammonium, NH4+, those kind of things are going to always be classified as ionic compounds. Now, molecule is for anything with a covalent bond in it. So we're talking about things that are covalently bonded are going to be non-metal compounds like carbon dioxide, water, methane. Those are all covalent compounds. Now, molecules also, because our diatomic molecules like oxygen has a covalent bond in it, those are considered molecules too. So O2, Br2, any of the diatomic elements are also going to be worded as molecules. All right, so going back over that mole map, we're going to look here at particles to liters example. This is also a something to something, so it should take us 3 steps to get through the conversion. Let's read through the information. Underlining also helps as you're going, so you can also highlight it if you're doing it in the Google document. Single replacement reaction was performed at STP, where iron replaced the hydrogen ion in sulfuric acid to form iron 3 sulfate, according to the reaction shown below. How many liters of hydrogen, okay, this is what I'm looking for, are produced if 9.25 times 10 to the 22nd atoms of iron react with excess of sulfuric acid? So here's my iron. This is my given information. That's important. And I'm looking for the liters of hydrogen gas. So these two, the sulfuric acid, I don't need to worry about. And the iron 3 sulfate, I don't really need to worry about. So starting over here, 9.25 times 10 to the 22nd atoms of iron. That's my given information. Now, before I can get to switching from my iron over here to my hydrogen and use the mole ratio, I have to be in moles. So the first step, of course, is changing the atoms to moles. So I take the atoms of the iron and I put them down here to going to 1 mole of iron. Now, because it's atoms, it's under the particle number, which is Avogadro's number. So I'm going to put in 6.02 times 10 to the 23rd here. So that's the first step. I change it to moles. Now, once it's in moles, I can take these moles of iron and diagonal them down to get rid of the moles of the iron and go to the moles of the hydrogen. And this is the mole ratio step. So this would be the mole ratio step. Switching compounds in the chemical reaction is always that mole ratio step. Now I look at the coefficient. This is a 3, so I put the 3 next to the hydrogen. Over here, that's the iron. This is a 2, so I'm going to put a 2 there. The last step, because it doesn't want moles of hydrogen, it wants liters of hydrogen. So I have to do one more step, convert the moles of the hydrogen over to liters of hydrogen. So I take the moles of the hydrogen and I diagonal those down to get rid of them, cancel them out, to the liters of the hydrogen. Now, according to the mole map, what we just talked about, standard temperature pressure, 1 mole of any gas is always going to equal 22.4 liters. So then we have this all set up nice to get ready to cancel. All right, so now I can cancel. I'm going to have atoms of iron cancel with atoms of iron. Moles of iron cancel with moles of iron. Moles of hydrogen cancel with moles of hydrogen. And I'm left with my liters of hydrogen. Now all I have to do is multiply everything on the top. So that 9.25 times 10 to the 22nd times my 3 times my 22.4. Then I'm going to divide by my 6.02 times 10 to the 23rd on my calculator, hit enter, then divide by 2, hit enter, and I should have my answer. Now, remember when you're entering these in on the calculator, you want to use your E button so that you get it to look like this. It's a much easier way than trying to do the times 10 to the 23rd where you might need to use parentheses because it'll get the order of operations out of order. It is the double E button on the graphing calculator, which happens to be the blue or the second button for the comma, which is right above number 7 on the calculator if you're using a TI. So I would use this notation in the calculator. It'll make sure that you don't get order of operations out of order. But when we calculate this, we end up looking here with 3 significant figures again. Okay, multiply it out, divide by, end up with your answer, and you should have gotten the 5.16 liters of hydrogen gas. And that would be the correct answer with the correct number of sig figs. Here is our unit, and here is our substance. All right, now looking at percent yield. Percent yield is a calculation that we use to see how much of the reaction produced in terms of and the efficiency of the reaction. Now, percent yield tells us how successful it is. It is usually never 100% in terms of producing 100% yield. The reactions, take place because of collision theory, where you have particles running into each other and they have to be oriented the correct way and they have to have the right amount of energy, that activation energy. So there's a lot of kinetics involved into why you're going to not yield 100% here. And we'll get to those kinetics later, but just know that that's probably, that's the reason why we're not going to end up yielding 100% in the lab itself, especially in a high school chemistry lab. The likelihood of yielding 100% is not going to happen. Conditions have to be adjusted in order to try to get the best yield that you can. And that's what this actual yield is talking about. That's what's performed in the lab. Okay, so this is where you're going to get your results from the lab. We also call it the experimental yield. Okay, so actual yield, experimental yield is the same thing, and that's what the person, the student, the experimenter gets in the lab. The theoretical yield is what you're going to get from your calculations. Like if everything was totally perfect in the lab, from the stoichiometry, you should get this number. You're never going to get that number, not in the high school chemistry lab. And in most situations, even in the industry and chemical reactions of industry, they have to adjust conditions to get the best yield for the amount of resources of reactants that they're using. And we'll talk about that also when we get to some other chemical reactions. So to calculate percent yield, really, it's just like the part over the whole times 100. So it's just like any percent kind of deal. The part is like, what did you actually get? What should you have gotten? What if you did everything perfect and everything, all the conditions were perfect, what should you have gotten? What would have been the whole times 100? So let's look at our first percent yield problem. All right, Jane's percent yield, calculate Jane's percent yield if she reacted 0.53 moles of KOH and she produced 44 grams of potassium sulfate according to this reaction. Now, she produces here, this is the key word here, she produced, that's telling you the actual, okay? So that's how it's worded in the problem. That's the experimental. So that's given to you. But we need to find, because percent yield is going to be actual over the theoretical times 100, right? So we need to find this value right here by doing some stoichiometry. We're going to set that up, starting with our given amount here. We have the 0.53 moles, and it says she produced 44 grams of the potassium sulfate. So that's what we're looking for. Now, because this is in grams, we also need to calculate this in grams. So we're going to do our T-chart here, and if you notice, we're starting with moles going to something. So this one should take 2 steps to finish, 2 steps. So we're going to set up moles of our KOH, potassium hydroxide, and first thing we're going to do here, since we're already in moles, we can go right to the mole ratio step and switch compounds. So we have moles of KOH going to moles of potassium sulfate. Now, looking at our balanced reaction here, and we have 1 mole of potassium sulfate to 2 moles of potassium hydroxide. Now that we're, switched over to this was our mole ratio step, switched over to the potassium sulfate, now we can change it over into the grams of potassium sulfate. So diagonal down that 1 mole, okay, to SO4, and the moles here, and then we go to grams, K2SO4. Now potassium is 39.10 on the periodic table, sulfur is 32.02, and oxygen, of course, is still 16 and times 4. So we're going to multiply that and add it up in order to get our molar mass of potassium sulfate. Okay, so this is supposed to be a 6. Apparently I didn't write that correctly. So it's 32.06 for sulfur. Once you add it up, it ends up being 174.26. And that would be the molar mass of potassium sulfate. So now we can cancel. So we have moles of the potassium hydroxide canceling with the moles of potassium hydroxide, the moles of the potassium sulfate canceling with the moles of potassium sulfate down here, and then we end up with our grams of potassium sulfate. Multiply the 0.53 times our 174.26, divide by 2 on the bottom, divide it out, and we end up, you should be getting 46 grams of potassium sulfate. Now this is our theoretical yield. So now we can complete our percent yield problem by going ahead and putting in our actual, our theoretical, multiplying by 100. So that's 44 divided by 46 times 100, and that ends up being 96%. And yes, I'm only going with 2 sig figs in my percent because this number's in 2 sig figs, that number's in 2 sig figs. So when you multiply and divide, you go with the least number of significant figures in your answer. Not all percent yield problems are like this. Some of them you have to work backwards on. So we're going to look at one where you have to work it backwards a little bit. All right, our last problem of this PowerPoint, looking here, where you're going to have to work backwards for some of the calculations. And once again, what does that do? You have to really look at the setup, look at what they gave you so that you can figure out where to start. All right, so we have 10 grams of silver reacting with excess nitric acid according to the reaction above at standard temperature pressure. The reaction yielded 68.3% of water vapor. How many liters of water vapor were produced by the reaction? Here I have my 10 grams of silver right here, and it wants liters of water up here, so we're looking for the liters there. And let's try to think about this. They gave us a percentage for the percent yield. So our percent yield, okay, which is going to give us our actual over the theoretical times 100. Okay, so we have this value right here, which is our 68.3%. We're looking for the actual. This is when we don't know, because it was the what is being produced. The theoretical we can calculate using stoichiometry, because we know 10 grams of silver to start with, so we can figure out how many liters we should end with if everything's perfect. So we can do the stoichiometry to figure out this theoretical yield. So we're going to go ahead and set that up. 10 grams of our silver. We're going to diagonal down the grams of silver, going to 1 mole of silver. First thing to do is change it to moles so then we can do the mole ratio. Once again, on the periodic table, silver is 107.87 for the molar mass. Okay, that's the first step. Now we can go from moles of silver over to moles of water using that mole ratio. Since we look here at the periodic, or I mean at the balanced reaction up here, we're going to have 2 moles of water for every 3 moles of the silver. Now that we have the mole ratio down, looking good, what we want though is liters of water. So I'm going to go from moles of water to liters of water. So 1 mole equals 22.4 liters of water. Now that we have that value set, we can multiply and divide and cancel. So our silver, grams of silver will cancel. Our moles of silver will cancel. Our moles of water will cancel, and we're left with our liters of water. When you multiply everything on the top, the 10 times the 2 times the 22.4, divide by your 107.87, enter, divide by the 3. Everything on the bottom, divide it out. You should get 1.38 liters of water. Now remember, this is the theoretical yield. And we want to know our actual yield, what is produced. So if we're putting that in there, we can just use like X for that. Over the 1.38 equals 68.3% times 100. Now, if you know percents well, you can just go ahead and change this over to 0.683 like this. Change it over to that, and then you have your 1.38 on the bottom. All I did really to change it over to the decimal over here is divide both sides by 100. You know, divide by 100, divide by 100, and then you have your setup here, and now it's an easy algebra problem where you multiply by the 1.38 on both sides, and that means that X ends up being 0.943 liters of water. That's what was produced. That is the actual amount. So this is the kind of percent yield problem where you have to work it backwards, because they gave you a yield percent to start with, and then you have to figure out what you have and what you can find from that. So it's part of the problem solving is, and knowing the concepts really well is not just doing the same pattern every time. Now you have to look at the different equations, figure out what you're missing so that you can work it forwards, backwards. All right, yes, and our answer is correct here. 0.943 liters. And hopefully you have a little bit better understanding of stoichiometry and percent yield now. So have a great day.